Here's problem 10.22. Identical particles are placed at the 50 centimeter and 80 centimeter marks on a meter stick of negligible mass. The rigid body is then mounted so as to rotate freely about a pivot at the 0 centimeter mark on the meter stick. If this body is released from rest in a horizontal position, what is the angular speed of the meter stick as it swings through its lowest position? So we have a meter stick. It has negligible mass, has no mass, which means we don't have to worry about the moment of inertia of the meter stick itself because it's got no mass. And it's going to swing down from horizontal to vertical. And on this meter stick are 2 point masses located at point 5, call that M, and point 8. Now the fact that they say that they're asking for angular speed means we'd probably have to think in terms of energy on this problem. And the fact that we have a meter stick of negligible mass means we don't have to worry about that, but we do have to worry about the moment of inertia of these point masses. So these point masses are going to be falling down to successive points like this, and this thing is going to be rotating like this. So if we're thinking in terms of energy, we'll think of this as being point A up here, and this as being point B down here. And we want to find the moment of inertia of this system. The meter stick has no mass, but we do have a moment of inertia due to these 2 point masses. That would be the summation of every mass multiplied by its distance from the axis of rotation squared. And this would be m times 0.5 squared plus m times 0.8 squared. So this is going to be equal to m times 0.25 plus 0.64, which would be m times 0.89. We're going to have to express the moment of inertia in terms of m because they didn't give us m. Hopefully m is going to cancel out somewhere. We'll have to keep that hope. Okay, so it is an energy problem. So we have that the kinetic energy at A plus potential energy at A plus any work done along the way should equal the kinetic energy at B plus the potential energy at B. In this case, there is no work done along the way. There's no friction or any other force. The kinetic energy at A, we're going to start from rest, so there is no kinetic energy at A. And we're going to say that our potential energy at B is 0. So when these masses reach these lower heights, those will be our 0 heights. Now the height for mass number 1 is going to be 0.5 meters, because when it goes down to that lower height, it's going to go down to a point that is 0.5 meters lower. And the initial height for mass 2 is 0.8 meters. This is going to fall to a position that is 0.8 meters lower. So we'll keep that in mind. But as far as point B is concerned, we define those heights as being 0, so we have no potential energy there. So strictly speaking, the potential energy at A is going to equal the kinetic energy at B. Potential energy at A is going to be mg height 1, which is 0.5 meters, plus the other mass, which is mg height 2, which is 0.8 meters. And that's going to equal the kinetic energy at B, which is going to be all rotational for this rigid body. So that's going to be 1/2 the moment of inertia times the angular velocity squared. Now we can see where we're going to get the angular velocity from this energy formula for point B. Alright, so we have mg times 1.3 is equal to 1/2. The moment of inertia we found to be 0.89 m, and this is times omega squared. Well, the m's cancel out. So yes, they didn't give us m, but it cancels out at this moment. And let's solve this for omega squared. So multiply both sides by 2 and divide by 0.89. So omega is going to be 2 times g, 9.8, times 1.3, divided by 0.89, and all this square root. So what do we get for that? 2 times 9.8 times 1.3 divided by 0.89 square root. I get 5.35 radians per second. So that is our angular frequency at the lowest position. Angular speed, 5.35 radians per second, the angular speed at the lowest position.